Hello, and welcome to the Chapter 3.2 online lecture on nonlinear models. So in the previous section, we talked about linear models. The meaning of linear models was that the differential equations were linear differential equations, but a number of systems have nonlinear differential equations. Fortunately, we can still solve these by using integration by parts. So recall from Chapter 1.3, we talked about coming up with a differential equation for the spread of a pandemic disease. And the basic idea was that a disease spreads proportional to both the number of infected people, y, and the number of uninfected people, which is the whole population minus the number of infected people. This is because the more uninfected people there are, the more opportunities for it to jump. And likewise, the more infected people there are, the more opportunities for it to jump. Mathematically, this means that the rate of change in the number of people who have the disease is proportional to, well, both the number of people who have the disease and the people who don't, p minus y. And as a differential equation, that just means it's equal to k times y, p minus y. It says we'll solve this later and find it is what we will call a logistic curve. Well, later is now. Let's do this with an example. Suppose that in the year 1340, at time t equals 0, 1 million people are infected with the plague, and 30 days later, 10 million people have the plague. And the population of Europe at the time was 78 million. Find a model for the number of people, y of t in millions, who have been in contact with the plague after t days. How long until Europe is 90% infected? So first we need to solve the general differential equation. We know that that differential equation is dy dt is k times y p minus y. And separating variables, that means that 1 over y times p minus y dy is k dt. And remember, as always, that you need to make sure the variables are completely separated, and here they are. And in this case, p was 78. So let's just write that as 78 and solve. So now we integrate both sides. Integral of a constant is just that constant times t. Don't forget the plus c. And the left-hand side, that is more challenging to integrate. This is an integration by parts problem. And remember that the idea of integration by parts is that we want to write it as a sum of two fractions, each of which will be easier to integrate. So where a and b are some, for now, unknown constants, we want to write this in this way. And the way to do this is to combine these fractions. So adding the fractions together by getting a common denominator, we have that. And then what we do is, up in the numerator, we gather like terms. So this is by minus ay is b minus a times y. And then plus 78a. And now what we do is we equate like terms. So 1, what we want to do is we'll write that as 0y plus 1. Those two are equal. And the reason for writing it that way is that now the coefficients must be equal. So b minus a is 0, and also 78a must be 1. So what we wind up with is a system of equations saying that b minus a is 0, and also 78a is 1. Okay, this first equation, adding a to both sides, that just says a equals b. And the second equation, dividing both sides by 78, a is 1 over 78. So we have that a is b is 1 over 78. So what we have found is that this fraction is the sum of these two fractions. And you can always check your work by just adding these two fractions. And if you add them by finding the common denominator, it is equal to this. And the whole point of integration by parts is to rewrite the integrand in a way where we can more easily integrate it. The right-hand side was kt plus c. Now integral of 1 over y is ln y, the 1 over 78 hangs out. And integral of 1 over 78 minus y is negative ln 1 over 78 minus y. And that constant hangs out. And now it's just a matter of solving for y. First thing that we would want to do is gather the y's inside of a single natural log. Recall log rules. ln A minus ln B is equal to the natural log of A over B. So this left-hand side, factoring out the 1 over 78, is equal to 1 over 78 times the natural log of y over 78 minus y. Okay, so we had 1 over 78 times the natural log of y over 78 minus y was equal to kt plus c. Multiply both sides by 78. And we can do our usual renaming of arbitrary constants. Now we will take e to the power of both sides. We want to solve for y. Exponential laws and our usual arbitrary constants. And we have y over 78 minus y is ce to the kt. Now we want to solve for y, so let's multiply both sides by 78 minus y. And we have this. Now be warned, we cannot rename this to c because the c is here too. And when we do a renaming, we need to rename c full stop. That means every instance of c. Otherwise, we're modifying the proportionality. So we need to keep that as is. Let's move yce to the kt to the other side, factor out the y. And now dividing both sides by this, we have solved for y. So doing so, y is 78 ce to the kt over 1 plus ce to the kt. That was just dividing both sides by this. Okay, good. So we finally solved the general differential equation. And now we need to apply the initial conditions to solve for c and k. So what were those initial conditions? Well, at time t equals 1, there were 1 million people infected. Remember, our output is in millions, so we would just say that y of 0 is 1. And at time t equals 30, 10 million people were infected, so y of 30 is 10. So plugging in, we have that that is the case. And at 30 days, now t is 30, 10 million people were infected. So that begets our two equations from which we can then solve for c and k. So our first equation, because e to the 0 is 1, becomes nice. And solving for c there, by multiplying both sides by 1 plus c, moving c to the other side and dividing by 77, c is 1 over 77. And then the second equation is this. That's a multiplication sign. We solve for c. C is now 1 over 77. And now to solve this, we can do a very similar thing to what we did to solve for y earlier, which is multiply both sides by the denominator, isolate e to the 30k, factor out, take the natural log, divide by 30, and we get 1 over 30 ln of 385 over 34. Solving for k there was just algebra, and it's very similar to what we did before. So the algebra here can get a bit messy. We can always check your work by asking Wolfram Alpha to do algebra for you. So I just entered that equation here and asked it to solve for k, and it solved for k here. And using a calculator to approximate that, it is about 0.081. So we've now solved for c and k, and plugging in, we finally have our model. And we don't like fractions aside fractions. Let's multiply this by 77 over 77. And that's much prettier. Now, without having to plug this into a graphing calculator, let's do a check to make sure it checks out. So at time t equals 0, this should be 1. 1 million initially. If we plug in t equals 0, it's 78 times 1 over 77 plus 1 is 78 over 78 is 1. And as it approaches infinity, it should be approaching all 78 million people in Europe. As we approach infinity, this 77 constant becomes irrelevant. So it's like 78 over 1 is 78, is the limit at infinity. So it checks out in both directions. And let's graph this to see what it looks like. And here's the graph. So initially, 1 million people infected. After 30 days, it should be 10 million. And it is. And it should be approaching all of Europe, all 78 million, and that is the asymptote. So this is what's called a logistic curve, and that's how we derive it and how it naturally occurs. And we could then solve for when this is equal to 90% of 78, for example. That was the second part of the problem. So that's just solving for when the output is 90% of 78. You can do this algebraically in a similar way to what we've been doing. And it looks like it happens after about 81 days. And indeed, 81 days, that looks like we're about 90% there. All right, so that's where logistic curves come from. They occur not just for spreads of pandemic diseases, but also things like population growth. When the population has limited resources, as is usually the case, one could set up a differential equation. It turns out to be the same. And population will grow in a logistic curve with the limited resources topping off the population of whatever animal that is. Here's the derivation of y. So we know that given unlimited resources, population growth is this simple differential equation that we've already dealt with. However, if resources are limited and there's a maximum population k and the proportionality constant is r, then assuming the growth rate decreases linearly to 0 as p approaches that maximum possible population, population growth follows this differential equation. This can be set up by remembering how we dealt in autonomous differential equations with stable equilibria. So if we're approaching k, and k is some maximum population, which the population would be stable, can't increase anymore, then that means that the rate of change must be 0. So if we plug in p equals k here, we have 1 minus 1. If p is k, that becomes 1. Gives another critical point in equilibrium at p equals k. And rearranging this by absorbing the r inside, for example, and multiplying by k, then it looks like this, where a and b are just other constants, which is the same type of differential equation as the spread of a pandemic disease, whose solution is that logistic curve. So we could solve constrained population growth problems in an identical way to what we just did. And why does this make sense anyway? Why should it be the same model as the spread of a pandemic disease? Well, a disease is a biological organism that has a population, and the constraint on the population of the disease is the number of humans. So just thinking of the disease as some population that grows in a constrained way, it would be this equation as well. And with this, we can even go further. So in some circumstances, we may wish to modify this. So for example, suppose that we wish to model the population of a fish, which is harvested at some rate h. So that rate h would be the change in the population of the fish per time, say per year. And then the differential equation would become this to model the fish population. So this is actually how differential equations would manifest in things like environmental engineering to figure out a safe harvesting level to maintain a certain population. Solving for h would yield an equilibrium solution for the sustainable fishing practices. Let's do one more example of a nonlinear differential equation. This is one where setting it up can be difficult, and that is the main point of this example. Suppose that two chemicals A and B interact in a 2-to-1 manner to form chemical C. So for example, 2 hydrogen and 1 oxygen make a water. And in this reaction, well, they'll react at a rate biproportional to both A and B. That's because the more oxygen there is, the faster it can react, and also the more hydrogen there is, the faster it can react. So that says that the rate of production of chemical C, perhaps water, is proportional to both the amount of hydrogen and the amount of oxygen, i.e. dC dt is K times AB. So let's do an applied example, and we'll solve and model how much C there is as a function of time. In this case, where initially there are 5 moles of A and 2 moles of B. So first, if we want to find a model for the amount of C that has formed as a function of time, we need to get this equation in terms of C only. How can we do that? Well, we know that A and B interact in a 2-to-1 manner, so that means that for every 2 moles of A that has reacted away, 1 mole of C has formed. So the amount of C that has formed is 5 minus the amount of A left. Initially, there were 5 moles of A, so 5 minus A is the amount of A that has reacted. The amount of A is decreasing, so if there are 2 moles of A left, that means that 3 moles have reacted away. And for every mole of A that has reacted away, 1/2 of a mole of C has formed, since it takes 2 moles of A to form 1 mole of C. So from this equation, solving for A, multiply both sides by 2, add A, subtract 2C, and we have A is 5 minus 2C. Similarly, for every mole of B that has reacted away, which is that numerator, 1 mole of C has formed, so the amount of C is 2 minus B over 1, and thus B is 2 minus C. This setup is the crucial part and the main point of this. And now that we have this, we can substitute each of these into this equation. We have A and B in terms of C only, and we will get our differential equation. So our differential equation, because A is that and B is that, this differential equation becomes this. And the reasoning and setups for different reaction ratios would be identical to this. Let's finish solving this problem though. So, same setup, initially 5 moles of A, 2 moles of B, they react in a 2-to-1 manner. At time t equals 0, the reaction has not yet begun, and at time t equals 1, 1 mole of C has formed. So from this, find the amount of C that has formed as a function of time. So we got that dC dt is K times 5 minus 2C times 2 minus C, with initial conditions that C of 0 is 0. Initially, the reaction has not yet begun, and after 1 minute, 1 mole of C has formed. So now we solve this differential equation. We'll get 2 arbitrary constants, K and the other arbitrary constant, and then we'll solve for K and the other arbitrary constant. So we have this. It is separable. Divide both sides by that right-hand side. Multiply both sides by dt. And now we want to integrate both sides. And as is often the case with nonlinear differential equations, we'll need to do integration by parts. So remember the way to do integration by parts. You first want to write the integrand here as a sum of 2 different simpler fractions with unknown, for now, numerators, which are constants. So I'll call them little a and little b. So this guy must be equal to a over 5 minus 2c, the first part, plus some other unknown constant over 2 minus c. And then what we do is we just add these 2 fractions together by finding the common denominator, multiply the second fraction by 5 minus 2c over itself, multiply the first fraction by 2 minus c over itself, and then add together. And we end up having this. And we'll always want to write our constant up here, if it's just a constant, as a linear equation. So 1 is 0 times c plus 1. That is not OC, that is 0c. The reason we'll want to do that is to equate coefficients. There's nothing fancy going on here. 0 times c is 0, so it just goes away. It's 1. Same thing. Okay, so the numerator on the right-hand side will gather terms together. We'll gather the c's together. So the coefficients of the c will have a minus ac minus 2bc. Factor out the c. And then the constant part, that's 2a plus 5b. And now we equate coefficients. So if these two are equal, we're all c. Then the coefficients must be equal. So we must have 0 is negative a minus 2b. And we must have that the constant part there is the constant part here. So we must have 1 is 2a plus 5b. Solving. We could do this by elimination, but in this case, it looks easy enough to solve by substitution because a is 2b from that equation. And then substituting that in for a, there, we have that 1 is 2 times 2b plus 5b, which means that b is 1/9. And then since a is 2b, that must be 2/9. So we got that a is 2/9 and b is 1/9. And we can always check our work by taking those and plugging them back into over here and making sure that it is indeed equal to what we started with. So let's do so, just to check our work. So if that is 2/9 and that is 1/9, then adding these fractions together, we have 4/9 minus 2/9c plus 5/9 minus 2/9c. The c's cancel out and we have 4/9 plus 5/9 is 1. So that is indeed correct. And we have rewritten this as a sum of two fractions, each of which we can actually integrate. So this was the differential equation we had. We want to integrate both sides, and to do that, we wanted to rewrite that integrand as a sum of two nicer fractions. And this is 2/9, 5 minus 2c, plus 1/9, 2 minus c, dc was k dt. And then we wanted to integrate both sides of that. The variables are fully separated after all. And this first part is not bad to integrate. It will be negative 1/9 ln of 5 minus 2c. You can always check your work by just differentiating, make sure you get that. Minus 1/9 ln 2 minus c equals kt plus, okay, we could call this little c, but that would be really confusing writing it because big C is the amount of chemical C that has formed. So let's choose a different arbitrary constant variable. Let's just call it d. So that's our arbitrary constant name since C is taken. We can solve this in a very similar way to how we solved the problem that resulted in a logistic curve, except this is a bit more complicated in the final solution, and it won't quite turn out to be logistic. So factoring out the minus 1/9 and using log rules, that's 5 minus 2c over 2 minus c is kt plus d. And we can do our usual renaming. We'll just rename that to k, rename this to d. And we have kt plus d, and then we can take e to the power of both sides. Rename again. And we have 5 minus 2c over 2 minus c is dect. And distribute. Remember, we cannot rename this to d because d is also over there. And whenever we rename an arbitrary constant, we need to do it to the arbitrary constant in all places where it is simultaneously. So we leave that as is. We'll isolate the c's on one side, factor out the c, and finally, the amount of chemical C as a function of time is that. And we had initial conditions. They were that initially no C had formed, and after 1 minute, 1 mole of C had formed. So from that first equation, plugging in 0, e to the 0 is 1, so it's 2d minus 5 over d minus 2, since that's 1, equals 0. Only way for that to be true is for the numerator to be 0, and thus we get that d is 5/2. So we had that d is 5/2, and our other initial condition was that c of 1 was 1 for our differential equation that looked like that. Okay, so we got d, and we know that c of 1 is 1. So plugging in 1 and substituting our d as 5/2, we know that the output must be 1. So solving for k in our usual way, k is the natural log of 6/5. So we are finally done. We have got that the amount of chemical C that has formed at a given time t is this. Let's multiply this by 2/2, just to eliminate fractions inside fractions. And also let's factor out the 10. And we finally have an equation for the amount of C that has formed as a function of time. Let's do a quick check and make sure it checks out. So initially, there had to be no C. And if we plug in time t equals 0, we have 1 minus 1 is 0. Okay, and how much C does there need to be as the chemical reaction progresses over time? Well, it was in a 2-to-1 manner. Initially, there were 5 moles of A and 2 moles of B. So those 5 moles of A could become at most 5/2 moles of C. And the 2 moles of B could become at most 2 moles of C. So as this chemical reaction progresses, at most 2 moles of C will be formed, and then there will be some A left over, because there's 5 moles of A, and only 4 of those will react. 4 of the 5 moles will react with 2 moles of B in that 4-to-2 manner, which is the same 2-to-1 manner as there. So the point is that the amount of C should be approaching 2 moles. And looking at this, if as t approaches infinity, these constants become irrelevant, and what happens is we just have 10/5, which is 2. So this kind of quick check, well, it's quick once you get the hang of it, seeing what the value is initially and seeing what the asymptote is to make sure it checks out with what we expect it should be, is a nice way of ensuring that it makes sense and you haven't made a mistake. And I want to point out that this is not a logistic equation, so it's not like population growth and what happens. Let's see what the graph looks like. There we have it. A logistic curve looks like this. It's approaching 0 to the left. This is not a logistic curve. And does it make sense? Well, initially, no C had formed, and then the reaction is going on, and it's approaching 2 moles of C that have formed. All right, so with that, we can model chemical reactions. And of course, there are so many other things that can be modeled with differential equations. It is an extremely powerful tool. So that concludes the lesson. Have a great one.